Okay, folks, this is Chapter 8. We are Section 8-4, and this is recording number 1. Okay, one more time here. Let me just kind of give you the overview. 8.2 was the z-test for a mean. 8.3 was the t-test for the mean. And I hope you remember that the difference is whether you know the population standard deviation or not. Now we're going to talk about the z-test for a proportion. So the z-test, just like up here, we're going to use the z distribution, the so-called standard normal distribution, to give us the critical values that we need in order to perform the test. But now we're going to talk about a proportion. So if you remember from before, we talked about proportion. So proportion is basically just what percentage. So the proportion of men and women, the proportion of boys and girls, proportion of Republicans and Democrats, whatever you're doing to divide into a group. Now, typically for what we're doing this for, our proportions is one or the other. It's binary. In other words, it's a situation where it's a binomial type distribution in the sense that it's one or the other. You're male or you're female. You're graduated or you didn't graduate. Okay. So let's talk about what do we talk about z-test for a proportion. Okay. There's a lot of hypothesis testing situations that involve proportions. It can be anything from healthcare type situations where you're trying to figure out what percentage of the people have high cholesterol, what percentage of the people have blood pressure problems, whatever it happens to be. Oftentimes you're going to be dealing with proportions. And what we're going to be doing is a hypothesis test involving a proportion, a population proportion, can be considered as a binomial experiment when there's only two outcomes. So that's the narrow focus that we're going to have, is there's only two outcomes: high blood pressure or not high blood pressure, sick or not sick, that sort of thing. Okay. This is something we learned before. The mean in a binomial distribution, the mean is NP. N is the number of data points. That's the sample size. And P is the probability of success of whatever it is that you're interested in. Okay. All right. So mu is NP. The standard deviation is sigma, which is the square root of. For this particular distribution, you can easily find it. It's NPQ. That's what it is for the binomial distribution. The typical example that we use is flipping a coin. You flip a coin, you get a head or you get a tail. That's a binomial distribution, and we can use you can use that as an example if you like. Okay, now remember, we talked about this before in a previous chapter. A normal distribution can be used to approximate the binomial distribution if n times p is greater than 5 and n times q is greater than 5. Well, that's a very easy condition to meet. Okay, so since we can use the binomial distribution to approximate, we can therefore use the standard normal distribution to test the various hypotheses. So this is the reason why we don't need a t-test. We're going to be using the z-test because the binomial distribution can be approximated by the standard normal distribution. Okay, so we got a little funny, kind of strange notation here. It's the same basic idea. You know, we have this observed value, take away the expected value over the standard error. So it's the same concept. In the numerator, it's how surprised are you? And in the denominator, it's what kind of a yardstick are you going to be using? Okay, but this is what we're going to be using for the formula. P, we usually say P hat right here. P hat is x over n. Now, here's where the notation makes you crazy. In this context right here, x is the number of successes. Okay, so let's say you're talking about heads and tails. X might be the number of heads that you got. So it's a number. You're counting the number of successes. Okay, so that in this situation, P hat is your observed value. You run an experiment and you come up with P hat. P hat being the proportion of the sample proportion. And it's the number of successes over n. Okay? P, without the hat, P is the population proportion. The population proportion is what you think it is according to your null hypothesis. This is what you think it is. Okay? And then the rest of them I think are pretty self-explanatory. This right here is this what's called the standard error. Okay, and he mentions right here about how do you get this formula. It comes from this formula. It's just a way, it's just the this is the normal formula, the standard formula we use for the standard normal variable. And this is obtained from that just by substituting n. For mu, we substitute np, and for sigma, we substitute root npq. So that's kind of left to the student at exercise 23. Maybe I'll try to do that when I get a chance and put that up on the video. In any event, in any event, what we have is this formula gives us the z score for our test. Okay, here's a very simple requirements. The sample is random, that's always the requirement, and then the conditions for a binomial experiment have to be satisfied. So that's something that we already know. And then this right here has to be satisfied. Okay, so let's take a look at these things. Let's take a look. This is talking about something a little bit politically incorrect, talking about obese young people. That's kind of, we call that body shaming nowadays. But we could just as easily make it, instead of being obesity, we could make it diabetic. We can make it heart conditions. We can make it any number of things, okay? So in any event, the researcher says, hey, listen, based on the information that I got from the CDC, 17% of young folks have this condition. To test this claim, she's going to select 200 people the same age, the appropriate age, and she says, okay, I picked 200 people and 42 of them had this condition, okay? At alpha equals 0.05, is there enough evidence to reject the claim? Okay, so what's the scenario here? Somehow, some way, this researcher gets his information, or it's published somewhere. It doesn't matter how we get it. It's just something that we want to test. 17% are obese. Boy, that seems like a lot. I'm not sure that's true. Let me see if I can challenge that. So let me pick 200 people of the appropriate age, and let me do a body mass index or do whatever, and let me find that 42 of them have this condition. Okay? So is this enough evidence to reject the claim? So here we go. Here's the hypotheses we have to come up with. The null hypothesis is that P is equal to 0.17. Where does that come from? Right here. It says the claim is that 17%, in other words 0.17, have this condition. The alternative hypothesis, the so-called research hypothesis, is that no, it's not 0.17. I don't know what it is, but it's not 0.17. So since this is an equal sign here, or I'm sorry, this is a not equal sign here, since it's a not equal sign, this is a two-tailed test. Okay, so just like we did before, we got to find the critical values. Alpha is 0.05. That's what they said right here. It's a two-tailed test. So the critical values, you got this cartoon right here. You got a critical value that's going to give you 2.5% here and 2.5% here. The 2.5% here and 2.5% here adds up to the budget of 5%. We already know from doing this previously that we using that Z table, the critical values, there's going to be plus and minus 1.96. So these are our critical values here and here. We do the experiment. For crying out loud, make sure you write down the formula every single time. P hat is our test data. That's the X over N, that's a number of successes over N. So when we say X is a success, what we mean is it has whatever value, whatever characteristic that we're interested in, whether it's obesity or positive COVID virus testing or diabetes or high blood pressure, or you flipped a coin. It doesn't matter what it is. The success just means it has whatever characteristic that we are concerned about. So the the 200 people that she tested, 42 were obese, so that's 42 over 200, so that's 0.21. Okay, P, that's the, that's what is claimed to be, that's what's claimed to be the population percentage, is P is 0.17. Okay, so you look at this and you say, okay, it sure looks bigger. 0.21 is bigger than 0.17, but that's not enough. It's not enough to just observe that this is bigger than this. You have to find out whether or not it is statistically significant bigger. Okay, so we got P. We also need Q. Okay, that's coming in the formula here as well, right? Coming here. We got to have P. We got to have Q. We got to have N. Here's P again, and then we also need P hat. It's only about, okay. So Q is always just the complement of P. So if P is 0.17, Q means the probability of failure. So P is a probability of success, Q is a probability of failure. So heads and tails. So it's 1 subtract P, which is 1 subtract 0.17, so that gives me the 0.83. Okay, so now make sure you write down the formula, you plug in the numbers, and here you are, 1.51. So 1.51 is your test value. That's right here. That does not exceed the critical value. Therefore, this is in the non-rejection region. Therefore, we say there is not enough evidence to reject the claim that 17% of young people are obese. Okay? Now you can see why someone might say this, right? You can see why someone might say, hey, wait a second, you say that 17% are obese. I just picked these people at random. I took 200 people at random, and I got 21% are obese. I think your estimate is low. I don't think it's 17. I think it's higher than 17, or if it isn't higher, it's got to be something different. Okay, so you can see why somebody would say this, but you also can see that given the variability, the yardstick that we have at the bottom here, it's not different enough. It's not statistically significantly different. So that's where this "how surprised are you" business comes up. You're surprised, boy, it's a long ways away from the expected value, but it's not that far away as measured by this yardstick that's in the bottom here. So that's kind of how I always look at it. And you know me, I can't remember formulas, so I just follow my intuition. Okay. Okay, I'll take a quick look at the next example here. A medical issue. I always like the medical ones. We got 21% of the babies are cesarean. The researcher thinks, no, I don't think it's 21%. I think it's less than that. Okay, I think my hometown is less than the population percentage of 21%. Okay, so I'm gonna challenge this. So the null hypothesis is that it's 21%. My alternative research hypothesis is that no, I think it's less than 21%. I got to find the critical value, which easily enough I can get. It's right here. That comes from going to the table. Alpha is 0.01, is a one-tailed test, so the critical value is negative 2.33. That just comes from the table for the z values, which you've done several times. Okay, so here's the formula. Write down the darn formula, plug in the information, you come up with a number here. That's the test value. So here's your test value, here's your critical value. The test value does not exceed, doesn't go past the critical value, is not in the rejection region. So we say there is not enough evidence to support the claim that the proportion is less than 21%. We do not reject the null hypothesis. So that's all we can say. All we can say is we're not going to reject the null hypothesis. Okay, so I'll let you do the next one, basically the same idea, and then the next one, same idea. Okay, excuse me, this one they want to use the p-value, so I'll do the p-value one, but we're going to do that in the next video.